Okay, thank you. First of all, I would like to thank the organizers for inviting me to this conference. It's always a pleasure to be here and have the opportunity to present my research. I would like to present some result, which is a joint work with Menachem Magidor. It is about a model of the stationary set reflection and the tree property at Alephℵ2+1. Now, as you know, the stationary set reflection and the tree property are two strong properties that can consistently hold at small cardinals. And the problem of how to force those properties at successors of singular cardinals has received quite a lot of attention. But many forcing techniques were proposed, but none of the forcing techniques proposed before seemed to determine a model of both the stationary set reflection and the tree property simultaneously holding at the successor of a singular cardinal. So the result that I would like to present shows that there is a model in which we can have both these properties at the successor of a singular cardinal, which is precisely Alephℵ2+1. And we will see why Alephℵ2+1, and we'll see that this is a special cardinal that can simultaneously satisfy several strong properties of that kind. So let me start by recalling you the definition of these properties. The tree property at a regular cardinal kappa is about kappa trees. A kappa tree is a tree of 8 kappa with levels all of size less than kappa. And so we say that kappa has the tree property if every kappa tree has a cofinal branch, namely a branch of size kappa. And the tree property at kappa is denoted by TP kappa. Okay. The stationary set reflection at kappa is defined as follows. Let's take let S be a stationary subset of kappa. We say that S reflects if for some ordinal alpha below kappa we have that S intersection alpha is stationary in alpha. And so the stationary set reflection at kappa says that every stationary subset of kappa reflects. And I will denote it by ref kappa, REFL kappa. Okay. So the reflection of stationary sets fails at successors of regular cardinals. In fact, let's introduce a notation for the set of all ordinals below some cardinal lambda that all have cofinality kappa. Let's denote this set by E kappa lambda. If kappa is a regular cardinal, then E kappa kappa plus is a stationary subset of kappa plus then that doesn't reflect. So the stationary set reflection fails at successors of regular cardinals. On the contrary, it can consistently hold at successors of singular cardinals, assuming, of course, Lush cardinals hypothesis. In fact, Magidor proved in 82 that assuming the consistency of infinitely many supercompact cardinals, it is possible to force a model of the stationary set reflection at Alephℵ+1. Okay. It is also possible to force the tree property at Alephℵ+1, and actually there is quite a huge literature on the subject. There are many forcing constructions that have been proposed to get the tree property at Alephℵ+1. The first one was given by Magidor and Cella in '96. They proved that they proved the consistency of the tree property at Alephℵ+1, assuming large cardinal hypotheses that are below the existence of a huge cardinal and two huge cardinal. Here to simplify, I just wrote the two huge cardinal, but the assumptions are actually weaker. Then later this result was improved by Sinabova, who proved the consistency of the tree property at ℵω2+1, assuming weaker large cardinal hypothesis, namely assuming the consistency of infinitely many supercompact cardinals. Okay, now the point is that other constructions were investigated, but none of those constructions seem to determine a model of both the tree property and the stationary set reflection at ℵω+1, nor at the successor of a singular cardinal, of a small successor of a singular cardinal. Because indeed all the forcing constructions involved in these results, they all seem to add a bad scale at ℵω and the stationary set that doesn't reflect. So Magidor and I proved that, recently proved that we can actually have both the stationary set reflection and the tree property at the successor of a singular cardinal, and this is ℵω2+1, assuming the consistency of infinitely many supercompact cardinals. The model where we have this result, it was an old model by Magidor and Cella, defined in '94, where they proved that ℵω2+1 can consistently have it can consistently satisfy a strong form of reflection that I'm going to talk in the next slides. And so we actually, what we did was just to prove that in the same model we can actually have the tree property at also the tree property at ℵω2+1. And whether the same can be done for ℵω+1, this remains an open problem. So let's see what is this strong principle of reflection that occur at ℵω2+1 in the Magidor and Cella model. This can be stated as a two-cardinal principle, denoted delta kappa lambda. So let's assume that kappa, let's assume that kappa and lambda are two cardinals, such that kappa is less than lambda. Delta kappa lambda says that given a stationary subset of lambda, all of whose ordinals have cofinality less than kappa, and given an algebra on lambda with less than kappa many operations, we can find the subalgebra of the algebra that have order type regular cardinal below kappa, such that S intersection A prime is stationary in the supremum of A prime. So given a stationary set, given an algebra, we can find the subalgebra of order type regular cardinal below kappa, such that the stationary set reflects on this subalgebra. Okay. And obviously this principle, it implies the usual stationary set reflection, namely if kappa is a singular cardinal, then delta kappa kappa plus implies the stationary set reflection at kappa plus. But this is a richer principle that implies several compactness properties, namely, let's say, consequences of the weak compactness theorem for L kappa plus kappa plus. I can be more precise and I can give some examples, which I hope are stated correctly, because they weren't explicitly stated in the paper. But delta kappa kappa plus implies that every almost free abelian group of size kappa plus is free, And almost free means that every subgroup of smaller size is free. Or it implies also that if G is a graph of size kappa plus and every subgraph of G of smaller size has coloring number some lambda, then G also has coloring number lambda. And if A is a family of kappa plus sets, all of size less than kappa, such that every subfamily of smaller size has a transversal, then A has a transversal. Now, the point is that this delta reflection at the successor of a singular cardinal, it implies a general compactness theorem for structures of different kind, abelian groups, graphs, transversals, etc. Okay. And so Magidor and Chala proved in '94 that assuming the consistency of infinitely many supercompact cardinals, it is possible to force delta ℵω2 plus 1. And there is something special about ℵω2 plus 1 because it is also known to be the smallest regular cardinal that can consistently have this delta reflection. So Magidor and I proved that in the same model we can also have another compactness property, the tree property. And as a corollary, so we have that we have a model of the stationary set reflection together with the tree property at ℵω2 plus 1. So I would like to present this model and briefly explain why we have both these properties in this model. And the idea is the following. If we take a singular limit of supercompact cardinals, lambda, then the successor, lambda plus, has both the tree property and the delta reflection. So if we to get our result, it is enough to turn lambda plus into ℵω2 plus 1 while preserving both properties. And the forcing, the Magidor and Chala's forcing that is used to get this model, it is a Prigry type forcing. It is a combination of diagonal Prigry with a product of collapses. And in particular, it will add an omega sequence of cardinals, alpha n. Each alpha n in the ground model, it is an inaccessible cardinal between kappa n minus 1 and kappa n. And together with that, we collapse cardinals. We collapse all the cardinals between kappa n plus plus and alpha n plus 1. And we collapse all the cardinals between alpha n plus 1 plus omega plus 2 and, okay, it doesn't work properly. Anyway, and kappa n plus 1. And below kappa 0, the forcing collapses alpha 0 plus omega to omega, and all the cardinals between alpha 0 plus omega plus 2 and kappa 0. And so in the end, each kappa n becomes an Aleph omega L plus something, and so lambda becomes ℵω2 and lambda plus becomes ℵω2 plus 1. And it is important for the delta reflection to leave gaps. It is important not to collapse cardinals between alpha n and alpha n plus omega plus 2. So I'm going to give the precise definition of the forcing, but first I need to introduce some objects. I need to prepare the ground model a little bit. By that I mean the following. As I said, we start by taking omega many supercompact cardinals kappa n. We can assume that their supercompactness is indestructible by directed close forcing. There is a technique by a lever that allows us to do that, to take a ground model in which those cardinals not only are supercompact, but they are also indestructibly supercompact. Then Okay, as I said, the forcing is going to be a pre-grid type forcing, a forcing that is close to a diagonal pre-grid forcing. So we will need ultra filters UN for each kappa n. But instead of taking these ultra filters from the supercompactness of these cardinals in the ground model, we define those ultra filters from the supercompactness of the cardinals kappa n in a larger model in which we already did the collapses. What I mean is the following: for every n, let Sn be this product of collapses. The product of all the forcing that collapse cardinals between each kappa m plus plus and kappa m plus 1, starting from n. This product is directed close, so in any generic extension via this forcing, kappa n remains supercompact by the indestructibility assumption. Okay, so in this model there is a normal ultra filter on p kappa n lambda plus, and this has a natural projection to an ultra filter on kappa n. One can actually prove that and we call UN the projection of this ultra filter, so this ultra filter on kappa n. One can actually prove that this ultra filter lives in V. Okay, and we need to fix another object. Let pi n be the elementary embedding corresponding to UN. We can inductively define in V a generic filter for this forcing, for the forcing that collapse all cardinals between kappa n plus omega plus 2 and pi n kappa n over n, over nn, sorry. Okay, so given those objects, we are ready to define the forcing. The conditions are omega sequences that are composed of a standard condition in the diagonal pre-grid forcing, namely there is a finite sequence of inaccessible cardinals followed by an omega sequence of positive one sets of inaccessible cardinals. Those are meant to select the possible ways to extend the alpha sequence. And then we had collapses. We have a sequence of GIs such that G0 is a condition in the forcing that collapses alpha 0 plus omega to omega. And the rest of the sequence is basically a condition in the product of the collapses that we considered before, the one that we called S0. And those are responsible for collapsing cardinals between each kappa I plus plus and alpha I. And finally, we collapse cardinals between each alpha I plus omega plus 2 and kappa I. Okay, anyway, the ordering is pretty much standard for pre-grid type forcings. So a condition P is stronger than a condition Q if the length of P is, namely the length of the lower part, it is at least the length of Q. And they have the same alpha sequence, the G sequence of P is stronger than the G sequence of Q, etc., etc., etc. Now, why do we have the delta reflection and the tree property in this model? The proof is quite long, but I can at least give a very brief idea of what happens. Let's start with the delta reflection. So let's assume that let's consider an algebra and the stationary set as in the hypothesis of the statement delta. We need to find the subalgebra where the stationary set reflects. So we can find, for some natural number large enough, we can assume that the algebra has less than kappa n many operations, and that the ordinals of the stationary sets all have cofinality less than kappa n. Okay, now instead of working in a p-generic extension, we work in the model where we took our ultra filters UN. Namely, we fix a generic filter GN for Sn that contains the G sequence of the conditions that we considered at the beginning. Actually, I'm cheating a little bit because we actually work in a larger model, but the point is that we work in a model where Kn is at least generically supercompact. Namely, we can find a generic elementary embedding for the supercompactness of Kn. And so in this model, we can define a fake version of the algebra and a fake version of the stationary set, and then we can use the supercompactness of Kn or the generic supercompactness of Kn to find the subalgebra where the fake stationary set reflects. And by working with the forcing, we can then find a subalgebra of the real algebra where the real stationary set reflects. This is just very the very idea of the proof, and which is quite long. For the tree property, what we actually prove is that we don't actually prove that any generic extension of the forcing works. What we prove is that there exists a generic extension of this forcing, for this forcing, where ℵω2+1 has the tree property. The proof is by contradiction. We assume for a contradiction that the empty condition forces that there exists a lambda plus Aron giant tree. Remember, lambda plus will become ℵω2+1, so we can actually work with lambda plus. And we work in, once again, instead of working in a p-generic extension, we work in an S0 generic extension. S0 was the product of the collapses. And the advantage of doing that is that in this model, K0 is still supercompact, and each Kn is at least generically supercompact. Then we consider, in this forcing, we can consider only those conditions of P whose G sequence is in this generic, in the generic G0. And this forcing has a very nice feature. For instance, we can say that two conditions of this forcing that have the same lower parts, they are compatible, or other very nice properties. And so then we use ideas from Sinabova's work on the tree property at ℵω+1, or also Niemann's work on the tree property at ℵω+1. We used ideas from this work to define step by step a sequence of pairwise compatible conditions in this forcing by working in the model VG0, and we define a sequence of nodes, a sequence of elements of lambda plus cross lambda, such that for every alpha less than beta, the weakest common extension of P alpha and P beta forces that U alpha is less than U beta. Okay, and this is done by first using the supercompactness of K0 to fix the length of the conditions that will work, that we will define, and then we use the supercompactness. Let's say that we find out that let's say that we fix the length and it is n, then we use the supercompactness of Kn plus something to fix the lower part, and then step by step we use the supercompactness of each Kn or the generic supercompactness to construct this sequence. So in conclusion, we have this. We have a model in which both this delta, the strong form of reflection, and the tree property hold. And we wonder, is it possible that maybe the delta reflection directly implies the tree property at ℵω2+1? Well, the answer is no. The two principles are independent. In fact, it is possible to build a model of the delta reflection at ℵω2+1 where the tree property fails at ℵω2+1, always assuming the consistency of infinitely many supercompact cardinals. And the idea here is always to consider omega many supercompact cardinals, kappa n, and lambda is again the limit of those cardinals. And what we do is first to force with, first we add the Suslin tree at lambda plus, then we force with the Magidor and Chelas forcing. The forcing that adds the Suslin tree at lambda plus is just given by conditions that are homogeneous trees of a successor 8 below lambda plus. And let's say that T is the Suslin tree added by this forcing. Then we force with Magidor and Chelas forcing, but where the ultra filters now they are taken from this model from and yes from oof yeah okay, from this model, namely in the model in V of R star T cross Sn, where T is the Suslin tree added by R and Sn is again the product of the collapses. This product can be shown to be equivalent to a directed close forcing. So for each n, kappa n is super compact in this model, and so we can properly define the ultra filters that we need, and so the forcing as before. And okay, so in conclusion, it is possible to have both the stationary set reflection and the tree property at the successor of a singular cardinal. It is actually even possible to have a strong form of reflection, this delta reflection that implies several compactness properties, and ℵω2+1 seems to behave like a weakly compact cardinal in this model. And whether it is possible to get a model, to force a model of the usual stationary set reflection and the tree property holding simultaneously at ℵω+1, this remains an open problem. And with that, I thank you for your attention.
Any questions?
Where do you use essentially that the collapse starts from ω+2?
Yes. Okay. Let me take here. I need to write down something. Okay. We can't collapse cardinals between Aleph n and Aleph omega. Aleph n plus omega plus 2, because when we get the subalgebra that does the work for the delta reflection, this is basically given. Okay, this is basically obtained in this way. In the original proof by Magidor and Chelas, they didn't use elementary embeddings, but I think it is more simple to explain it in this way. So the subalgebra, let's say that Jn is the elementary embedding that we get from the supercompactness of kappa n in this model. The subalgebra is obtained by basically by considering the pointwise image of lambda plus. And in a model in which this set has a size alpha n plus omega plus 1. So if we collapse, that's the reason why we cannot collapse cardinals between alpha n and alpha n plus omega plus 2, because if we do that, then the subalgebra will end up having the wrong order type and the argument wouldn't work. Well, but you had a model of the stationary set reflection at Aleph omega plus 1 with, without leaving gaps. So I had the impression that the problem is more about the algebra and the subalgebra, but I don't know. It's okay.
There it's very specific. It's either or. It collapses everything.
Mm-hmm.
The Aleph omega plus 1 case, it's important you collapse. If you kappa and kappa plus 1, collapse all the cardinals. You don't leave anything.
Okay. Anyway, it is a priori it is possible to get the stationary set reflection and the tree property at Aleph omega plus 1, but the delta reflection, it is proven that it's not possible to get it below Aleph omega squared plus 1 at a regular cardinal.
So, no more questions? Okay, so let's thank Laura again.